Okay, good evening. I usually organise these talks. My name is Simon Campbell, as Alex just said. Been co-organising for a number of years with also Hamid Muradi, who's in the audience tonight. And I thought I'd take advantage of the situation and give a talk on myself, and sell the message of stars, just how important stars are. So basically, this talk is about stars and how great they are. So take-home message is stars are cool, basically. I can be hot too. Some of them are cool. Okay, just a little overview of my talk. I'll first go into what starlight is exactly and how it makes the universe colourful. Then I'll talk about the journey of starlight and how from that we've learned about the vastness of space. Then I'll explain exactly how we read or decipher the starlight to get the information out of it so that we can make these grand statements and learn about the universe. And then if I have time, I'll go into briefly some of the things we've learned about starlight and what the future holds. Learn from starlight. Okay. So the first part is basically what is starlight. And this is a valid answer, I think. If you go outside and look up at the sky tonight, you'll see stars giving off light. So that's our first experience with starlight. And that's how I started, camping out in the country and just being amazed by the Milky Way and all the different stars. But tonight I want to go into it in a bit more depth. So this is the night sky in about 1 hour. And I have my first quiz question, I have a few of these, is what is the brightest star in the night sky? I'm sure there's lots of people could answer that here. Sirius. There's Sirius up there. So this is 9 p.m, I think it is, 8:47 down there. So if you go and look north, you'll see Sirius up there. Now I'm going to pick on Sirius. It's going to be our pet star for the night, and we're going to track its light and decipher what's in its light. So there's my mock-up of Sirius, a nice bright blue star. And there's Earth, not to scale, nothing's to scale here. So the first thing you notice about the star is that light goes out in all directions. A star is basically just a big hot ball of gas, and it's radiating light as well as other things from all over its surface. So actually most of the starlight doesn't get to us. It either goes out to the other side of the universe or misses us completely just because of the trajectory. But some of it does reach us, and this is what we see in the night sky. And so I'm going to call this a light beam. Not strictly true, but this is just how I'm going to go through the talk with this light beam. And this is the light that actually makes it to us on Earth. So I've put the light beam up the top of all my slides so we can remember what we're following here. So it's Sirius, and there's our beam of light. So what is this beam of light? Basically, it's electromagnetic radiation. So the question is, what is that? Some of it is light, and that's what we see. And that's because our eyes are tuned to seeing that part of the electromagnetic spectrum. But a lot of it's not light. So a lot of what comes from the star is actually in the form of radio waves, ultraviolet waves, infrared, X-rays, even microwaves. But it's all just energy travelling in this way, in waves. And so we use a lot of this in our daily life. So when we have a wireless internet connection, we're putting out electromagnetic radiation through the house or through the workplace. And we use it for radio. This is the earliest wireless. You've got television, and we even cook with electromagnetic radiation. So what are these electromagnetic waves? Well, here we've got a sort of sketch of a wave. You could think of it as an ocean wave. But basically, the main point here I want you to take is that the distance between two peaks is the wavelength of a wave, and that characterises the particular waves. And there's a whole host, a whole spectrum of these waves. So as I said, the main differences between the different electromagnetic radiation is the wavelength, but it's also the energy that's contained in those waves, and they're related, these two things. So we basically put them into two buckets. We have low energy electromagnetic waves, and high energy. And so there's some familiar examples. Low energy, we have radio waves and light. high energy, we have UV and X-rays. And so these are familiar. You know that UV can damage your skin if you're exposed to it for too long. It's because it's high energy. And X-rays, which can go straight through your body and also damage your body as well. So they're high energy. And they have shorter wavelengths. So you're probably all familiar, everyone's familiar with prisms and rainbows. So this is actually the splitting of visible light, the visible part of the electromagnetic spectrum. So in here, this is the cover of Pink Floyd album way back. We have white light coming in here, and then you can split it up into its constituent colours. And this happens in nature through rainbows in our atmosphere. Now you can actually do this for the entire electromagnetic spectrum. So all different wavelengths and all different energies. So here's the full electromagnetic spectrum. We start down here with the high energy stuff. So they're gamma rays, X-rays, UV. So stuff that will hurt you. And then there's infrared, microwave, radio, and you get weaker and weaker and longer wavelengths. But you see this little bar of colour in here, this little rainbow. That's actually what we can see. And I've just expanded out that little bar there. And so that's the rainbow. But you actually you can have a rainbow of the entire spectrum. So you can have a rainbow, a UV rainbow, an X-ray rainbow, radio rainbow. So you can spread out into all different rainbows that we can't see. We just happen to be able to see in that little bit of the spectrum. So there's a bigger world out there. It's only if you have special glasses or special telescopes that you can see the other parts. That's just what our eyes can do. And just to drive that point home is about the wavelengths. So this is the visible spectrum. So red, orange, yellow, green, blue, all the way to violet. And you can see that the wavelength is changing. So you're getting shorter and shorter wavelengths, higher energy. So down here you've got UV, which is very short wavelengths. And that's packing the most punch. Okay, so now we've got our homework out of the way. So we're going to have a look at Sirius's light again. Here's the light beam. And I'm going to put a prism in the light beam. And then I'm going to, if I can press the right button, I'm going to redirect the light with a mirror or something down here into a telescope, and then I'm going to plot what we call a spectrum. Now, this is spreading out all the light, or all the electromagnetic radiation. So on the vertical axis, I've got brightness, just how bright it is in that particular wavelength. If it's bright in red, or it's bright in the UV, bright in radio. So we'll find out by plotting in this plot. And I've along the bottom we have wavelength, and I just marked out a few key things like here's the UV, this is the visible light that we can see, and this is infrared. And the star, Sirius's light, which is just sort of mocked up here, is a curve. And the interesting thing is where it peaks. So with this particular star, and a lot of stars, the spectrum peaks in the visible. So that means it makes a good rainbow because you can spread out a lot of visible light. You have a lot of brightness for the rainbow. It also tells you, if you look at exactly where the peak is, it tells you sort of what colour the star will be. And not surprisingly, Sirius is peaking in the blue, so it's because it's a blue star. So we can extend this. So a star's colour depends on where that peak is, right? So we've got Sirius there, which is a blue star. Many stars peak in visible light, as I said, but even if they don't, they'll have some of their spectrum in the visible, usually. Not always. So you do tend to see some colour. Oops, jumped the gun there. So here I've put in the heavy black line is me just drawing in another spectrum as an example. And this one you can see where it peaks. It peaks sort of in the red, and that's a red star. And so you can see stars actually come in different colours because of how their spectrum is distributed. And then we'll go back to the night sky. Now this is the Southern Cross. Everyone's seen that. These are the pointers. And you can see in the Southern Cross you have 5 stars. 2 of them are actually red and 3 of them are blue. And that's because that's where the main part of their spectrum is emitting. So these are red giants. I'm actually not sure exactly what stars they are. I assume they're red giants. And these are blue giants. they're so bright. And then if you look even closer, you can see this one may not be a star. There's more blue stars, there's more red stars, smaller, less bright. But if you look at the background, there's lots and lots of little sort of whitish stars. And that's your most common star in the universe. And that is a star like the sun. So that's actually most of the stars in the sky. They're not just these big bright ones. There's a lot of stars like the sun that are just sort of whitish. Maybe a little bit yellow, maybe a little bit blue, but generally sort of whitish. And not very big and bright. So you'll see always this background of stars. Also there's things way off in the distance which don't look so bright. So it's actually quite a colourful universe. So if you go out tonight, I think there's not too much cloud. And if you look carefully, if you let your eyes adapt to the night sky, you should be able to tell the difference between the red star and the blue stars with your eye. And certainly you can in the country. And quite easily with a telescope, as many of you know. And so this is sort of a sketch of what these stars look like inside. And so you have the sun-like star. And the sun is not actually yellow like that, it's yellow-orange. It's a bit of an illusion that we get through sunsets. Red dwarf, blue giants. We also have red giants, orange giants, a whole range. And so here's another pretty picture from a telescope. And you can see these lovely blue giants. And these are usually massive stars, quite young. The red ones are usually older stars. So you can see there's colour out there. And this is the type of stars I work on. These are called globular clusters, about 1 million stars, all in a big ball, and they're all sort of born together. And so you can get really good demographics out of these, because you can look for how many old stars there are, how many young stars, and again you can clearly see the, I'll stick to one slide, one side. You can see the red giants, you can see the blue giants, but again that background of lots and lots of small stars like the sun. The bright ones sort of stand out more. And then if we look at galaxies, which are made up of billions and billions of stars, they have colour too, and this is mainly not just due to starlight, but it's largely due to starlight. So you have these blue galaxies and you have these red galaxies. And usually we just say this is because there's a lot of young stars. So this would be like a star-forming galaxy. So there's actually young stars forming, and they're still blue and young. And a red galaxy is usually an old galaxy. It's not forming stars, so all the stars have aged. They have an aging population. So it's a bit like countries. Okay. So now we know there's lots of colourful stars out there, and we've had a look at what starlight actually is. We'll talk about the journey of starlight and what it tells us about the vastness of space. Okay, so we go back to our pet star Sirius. So the immediate question is, okay, how long does the light take to get to us? That, of course, depends on how far away the star is, since we all know that light travels at a constant speed of c. But how fast exactly is that? So this is another quiz question. It's 300 kilometres every something. Does anyone know? Second. We've got too many experts in the audience. That's right. That's 300,000 kilometres in a second. And that's about the distance to the moon. So light takes about 1 second to get to the moon, or vice versa. So yep, I said that. So this means that the stars we're looking at are not actually how they are now. They're how they are in the past. So what we see in the night sky, oops, sorry. This is a new pointer. What we see in the night sky is, in effect, looking back in time. Because that light left the star maybe 5 years ago, if it's a close star. So it took 5 years to get to us, through our eyes. But in that 5 years, something may have happened to the star. It may have disappeared. An alien might have, towed it somewhere else, and it's not there anymore. But we still see it in the sky because we're looking at history. Now, this also is true of the sun, which is our closest star, of course. And it's our best studied star because it's so big and bright. My next quiz question is, how old is the sunlight that we see on Earth? Got some very exact answers in the audience. Well, it's 150 million kilometres. So if you do the maths, it takes 8 minutes to do that journey. 150 million kilometres at the speed of light, it's 8 minutes. So the sun we're looking at is actually not how it is now. If something happened to the sun, we wouldn't know for 8 minutes. So next time you look at a sunset, possibly in Darwin, there's some nice ones up there, you might think that actually that's not what the star looks like now. That's how the star was 8 minutes ago. So that was Darwin 2012. But in 2012, there was something else taking a really nice photo. And that was the Hubble Space Telescope. You've probably heard of the Hubble Deep Field. Well, this is the Hubble Extreme Deep Field. I'm not sure what the next term they're going to use after extreme is. They've used ultra already. Super extreme. We'll come back to this scientific naming convention later, actually. So the extreme deep field, it's the same sort of areas as the Hubble Deep Field, it's a bit smaller. So they basically picked a sky where you can't see anything with a normal telescope. And then they left the shutter open, so they exposed for a long time, or many times, and then stacked the observations. But they looked at it for a long time, just to get as much starlight, just wait there and wait for the light to come to you, and record that with the digital camera. And this is what they saw. So far from being a blank piece of space, there's all sorts of stars and entire galaxies. This is a galaxy here. There's red galaxies. And all this is all at different distance as well, but most of it's quite a long way away. So you have and there's a little galaxy there, and side-on galaxies and face-on galaxies, all sorts of stuff. So next quiz question is, how old is the light that made that picture? It's a bit older than my picture. Does anyone have an idea? 12 billion. Sorry? 12 billion. I have 12 billion. It's an auction. Wish I had something to give you. Well, finally a question that almost right. Up to 13.2 billion years. So the furthest away object, they're all at different distances, is 13.2 billion years old, that light. It took us that long to get, took the light that long to get to us. So here we are looking way back in time. This is before the sun was even born. In fact...
Simon?
Yep.
That wouldn't be any of those large galaxies, though. It would be just a tiny little red spot somewhere.
Yes, that's right. Yeah. There's a whole range of distances and a whole line of ages in there, right? So you're looking back at different... So it's probably a record holder, this 13.2 in this picture. So it will be just a little red dot because it's redshifted, and I'll get to redshift later. So this 13 billion years ago so the sun is 5 billion years old. So this is 8 billion years before the sun was even born, before the Earth was formed. So this is a long, long time ago. And in fact, the current estimate for the age of the universe is 13.8 billion years. So we're getting close to looking right back at the start of the universe. So the next big question that comes to mind when you see a picture like that is, okay, that's a long way. How big is the universe? Well, we know that, again, light travels very fast. So the stars, as Perry rightly points out, if that furthest galaxy, it must be a galaxy because it has to be bright, sent its light out 13.2 billion years ago, and it's travelling at that speed. That's how far away that galaxy is. Now, I can tell you don't need to count it yourself, but there's 21 zeros there. That's a lot of kilometres. And actually, that's just half the story because, as I said, we're looking back in time. But in that intervening 13 billion years, the universe has actually expanded. So that galaxy is actually much further away. But you get the picture. It's big. Now, if you have a huge place, you need a huge ruler. And so we use the light year. It's one of the units. This is a unit of distance, not time. It's commonly mixed up. So 1 light year is just the distance that light travels in a year. And I'll just convert light speed to kilometres per hour. That's 1 billion kilometres an hour, so it's a pretty fast car. So in a year it travels about 9,000 billion kilometres, if I've done my calculation right. And so that's what a light year is, 9,000 billion kilometres. That's a long way. So next quiz question is, how far is the nearest star? I know someone will know that exactly. 4.3 light years. I've just approximated it to 4. So 4 light years at that speed. I think I've mucked up some units there, but that's okay. It's 36,000 billion kilometres away. So I did a Google and have a look at the current spacecraft speed records, which is a list on Wikipedia. And I didn't take the manned spacecraft records, because I took the unmanned ones just so we get a bit further out. So it turns out it'll take 145 million years to reach the closest star of Proxima Centauri. With current technology. Well, not even current. So people used to say, okay, we'll invent warp drive soon. And yes, that would get us there much quicker. The speed of light is warp drive. And you might be able to go 10 times. You might get warp 10, like in Star Trek. And so you're streaking through the stars. So you get to Proxima Centauri in about 4 years. And less than that if you have warp 10. But then the next similar galaxy to the Milky Way, which is Andromeda, okay, and that's sort of just a local galaxy. It's nothing like those ones in the Hubble Extreme Deep Field. It would still take, if you had warp 10, 250,000 years at warp 10 to get to the next major galaxy, right? So the next major city sort of thing. So we're not going to get there in any time soon. So this reminded me of this great quote from one of my favourite authors, Douglas Adams, The Hitchhiker's Guide to the Galaxy, where he says, space is big. You just won't believe just how vastly, hugely, mind-bogglingly big it is. I mean, you think it's a long way down to the chemist, but that's just peanuts to space. So it's very, very big. Okay, back to our pet star, Sirius, and a beam of light that's coming to Earth. There's a catch. The light has made it through all these things, you know, managed to avoid all those galaxies and dust, and it's made it to our solar system. But then there's a problem. Earth has sunglasses. And what do I mean by that? So, I mean the atmosphere. So we have this protective layer called the atmosphere, which is just like wearing sunglasses. You stop the harmful UV rays coming in. So this is a picture just illustrating what it does to sunlight, which is the same as what it does to starlight. So basically, you have your sunlight, you have light beaming in here. 30% of it just gets bounced off the atmosphere. It doesn't even make it into our atmosphere. Another 20% gets a bit of the way into the atmosphere, but then gets absorbed. So it doesn't make it to the ground. So all we've got left is half the light from the sun, half the energy in the light. So these are our sunglasses, and if we didn't have these sunglasses, the atmosphere, we wouldn't be here. We'd just be fried by X-rays and UV, and wouldn't have life, basically. So I thought, okay, well, I wanted to have a look at what the atmosphere looks like from space, and some nice astronauts in the International Space Station has put this online. Some very nice pictures from the space station. And this is Earth, and those bright lights there are cities. And of course, there's the background star. So we managed to take fairly long exposure, just flying through space at God knows how fast. Anyway, the thing is, this is the Earth, and you can see that the curvature, this is really zoomed in. So this layer is actually very, very thin. We're sort of floating through space with this tiny little layer with tiny little very thin sunglasses protecting us from basically getting fried by X-rays and UV. So don't be scared. It actually works. Okay. So what do Earth sunglasses do? Like I said, not all the starlight makes it to the ground. So that's a bit of a problem if you want to study stars. Right. This is one of the key reasons we put telescopes in space, is to avoid the atmosphere. And so here's a plot. By now we're experts on the electromagnetic spectrum. So we've got the nasty stuff here, X-rays, gamma rays, UV, and we've got the less scary stuff here, infrared, light, radio. And basically this tells you how far each part of the spectrum gets down into the atmosphere. So you can see there's huge swathes here where you don't get anything at the ground. So, for instance, especially the high energy, which is good. So we don't get X-rays, for instance. We don't get X-rayed every day. UV is partly blocked. But then you see there's this little torrent here that reaches the ground. And that's the visible light and a bit of infrared. And that's why we have telescopes, optical telescopes like this, on top of mountains to get even a bit above the atmosphere as well, a bit up in the atmosphere. So that's why you have these types of telescopes with domes and big mirrors. And then some clever people figured out, if you go high enough into the atmosphere, you can catch some of this infrared. You put a telescope in an aeroplane, and they actually do this. They open up, they have a jumbo jet, they have a big door, and then there's a telescope sticking out the side, looking at these wavelengths. So you don't have to go to space, it's a lot cheaper. But then you see that there's this big torrent here, nice wide window in the electromagnetic spectrum, and this all gets to the ground as well. So this is actually the lower energy stuff, like radio waves, so this centimetre wavelengths, millimetre wavelengths. And that's why we have these types of telescopes. So these are like the dish. So they collect this stuff that hits the ground. So this is why we have these types of telescopes. And then we have this barrage of telescopes. Hubble sort of spans the visible and a bit of infrared and UV. So it can take nice visible pictures from space, which has been really, really nice. Okay, so my part 3 is reading the starlight and also deciphering it. Step 1, obviously, is you need to collect the starlight. So you build a telescope. So that's what Galileo did. He didn't invent it, but he improved it and he pointed it to the night sky. His telescope was 3.7 centimetres in diameter, but he made lots of discoveries. For instance, he's managed to see the moons of Jupiter, and they're named after him, the Galilean moons. And he looked at sunspots, for example. Now we have these modern backyard telescopes, something like 15 centimetres. Some people here will have bigger ones, but that sort of order. And they're much more powerful than what Galileo had. And then in the 60s, 70s, these 4-metre class telescopes were built. So that's 4 metres, I guess, is about from the ground to the top of the screen there, something like that. So it's a telescope mirror like that. And that's the Australian one. So that was sort of top of its class back in the day, in the 70s and 80s. In terms of size, it's still top of its class in terms of instruments. So I'll be using that later this year. For the current generation, 8 to 10 metres. So this is something like 4 metres. It's twice. These are huge telescopes, giant mirrors. And that's the dome for one of. They've actually got 4 of these. That's a big telescope in Chile. So my next quiz question is: what is this telescope called? This is a scientific. Sorry. It is called a very large telescope. Not a very exciting name, although they do have individual names which are nice, but it's called a very large telescope. Now the next generation is already being built. Okay, this is very exciting. They started building this late last year. These guys have mirrors that are 40 metres in diameter. Now you can't make a single mirror like that, so they make it in segments. But it's just hard to imagine how big that is. But what I've done here is, this is a sort of artist mock-up. I put a car in there, which is helpful, so you can see how big this guy is. So next quiz question is, what is this telescope called? Extremely large telescope. That's right. It's very, very creative. But wait, there's more. This beast, which is already sort of on the horizon, they've drawn it up, and they've made nice, pretty pictures. 100-metre mirrors. So this is I don't know, it's starting to get the size of a football field, I guess. And there's a car there.
Let's have a guess. Ridiculously large.
Close. 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 So this is the actual dish here, right? This is a secondary mirror for those people that have telescopes. And that's, I think that's like 8 meters or more. This is like the telescope of today, and this is just... so do we have any...
What sort of scaffolding for?
Overwhelmingly large telescope. Well, and they even have an acronym. It's called OWL. Right. So that's the future. So we're going to collect a lot of light. Sorry?
What's the mirror made of?
Mirror made of? No. I think how they do these things is they make, the biggest mirrors they can make is about 8 to 10 meters, and then they make segmented ones. They actually are made of glass. I've been to a mirror factory in Arizona, which is actually under a football stadium. And they can only make particular size mirrors because under the football stadium it's quite large, but they start off with making small mirrors. And now the size of the mirror they can make is limited by what they can get out the door of this football stadium. But they're actually made of glass, but it'll be special glass. And they have to they do this whole polishing thing, and it takes years. Yeah, if you go to the University of Arizona site, you can see exactly how they do it. But I'm not an expert on the instrumental side. Next thing we have to do is record that starlight so we can analyze it later. Basically, it's digital cameras, but they've got a lot more megapixels. This is for a 2-meter telescope. It's got 268 megapixels. So you just take a picture of a spectrum or just of the stars. Step 3 is to decipher it. Okay, this is where it gets exciting for me. There's a few ways to decipher starlight. One is through photometry, so brightness and colours. That's all it is really. And the second way is through spectroscopy. So this is dealing with a spectrum, as I explained in the first half of the talk. So basically, this is a global cluster that we saw before, so about 1 million stars. So you take a picture, and then you measure the brightness of all the stars, and you measure the colour of all the stars. And then you put it on a graph. And here's the brightness, and here's the colour. And it's quite amazing. You get this amazing tight sequences. It's not just spread out. It's very tight sequences. And so the first people who did this must have been just shocked. It's like, wow, that must be telling us something. and indeed it is. So what it's telling us in here is that there's a lot of stars that are not very bright and sort of yellowish. And these are sun-like stars. These are most of the stars in the universe. And then you have these bright red giants, which we can see in the sky, and then you have these blue giants. And there's a few other things. So basically we eventually put together a picture using computer simulations as well, that this is a life cycle. So you start off as a main sequence star, and then you become a giant, and then you become a blue giant, and then you become a giant again, and then you die as a white dwarf in this case. So it's got a lot of information just by doing that, just by taking a picture and measuring colour and brightness. Just go briefly into life cycles of stars. I wanted to go into this more depth because this is my field, but I'll just give you a little overview. So this is the birth cloud. It might be a cluster of stars, maybe 100 stars or 10,000 stars get born. Some of them, they have a range of sizes, a range of masses when they're born. So the average star, say the sun, is born, spends most of its time like this, grows to become a red giant. This is sort of its old age, and then becomes what we call a planetary nebula, which is a historical naming convention, nothing to do with the planet at all. And then ends its life as a white dwarf, where it's not burning, not doing any nuclear burning in the core, it just cools off and dies. Becomes a sort of ash of the universe. Now, if you're a massive star, this is what Alex Hager works on, who introduced me. These guys become red supergiants or blue supergiants, but they end their lives by going supernova. They just explode. And the leftovers from those guys is usually a black hole or a neutron star. And we see these out in space. We see all of these. So this is our picture of how stars live and die. Okay, next way to decipher the light is through spectroscopy. As I mentioned earlier, the starlight can be spread out in a spectrum, not just the visible light, but I'll just use the visible light here as an example. So it turns out that some colour is actually missing, but some very particular colours. So you can see these dark lines in the spectrum when you spread it out. These are called spectral lines, and it's caused by the gas absorbing the gas on the surface. Some of this light. It turns out each line is actually caused by a particular element or molecule, if it's a cool star. So we can actually work out what the star is made of. So this is another thing we can learn about the stars, just through looking at its light. So for instance, I'm just making stuff up here, but that might be an iron line. There's certainly a lot of iron lines. So there's iron in stars. Calcium often comes in a doublet, so you have two lines. And then it's quite often we see gold, or europium, or silver, or uranium. So stars, and that's because that's where all this stuff comes from, right? It comes from stars. But I'm not going into that in this talk. So spectroscopy gives us elements. So this is the VLT, and this is one of my spectra that I took. This is a red giant star in one of those globular clusters. Okay, this is just an example. So this is just spreading out the light, just like that. But this is much more detailed, and you can see there's a lot of missing light. There's all these dips are lines, and all those dips are caused by different elements. And so basically the game is try to match what we know about the periodic table and try to work out what's in the star. And you get, for some stars, like the sun, for instance, you can get almost every element. It's quite amazing what information you can get. And then you multiply that by millions of stars now. We have these big surveys, searching the whole stars, trying to get all the chemical abundances. And you can put together a picture of the evolution, the chemical evolution of the galaxy. And this is a fairly hot field called galactic archaeology. Spectroscopy also gives us the speed of stars. This is through the Doppler shift. So just like a speed camera, held by this policeman, Australian, I think. So this is our star, and it's just emitting, say, a single wavelength of light, and you've got a spectrum like this. Now, this star happens to be moving. In this case, it's moving to the right. And what you can see, those wavelengths sort of bunch up, and that effectively comes on this side, it becomes a bluer light, and on this side, it gets a redder light. So this is blue shift and red shift. And what that does, it shifts all these lines to different colours. And from this, because we know the pattern of lines, we can work out how fast the star's going. So we've got a speed camera. And that's, in this case, this is a redshift, what I've shown here, which is very important for the expanding universe. So just as an example, this is a Hubble picture of a globular cluster, and they've done a little sample in here where they've looked at the stars and really measured their velocities in great detail, and then they've done a simulation forward in time. So these are all those stars, a simulation, and you can see each one has a number of dots. That's every 30 years. And so these stars are moving in all different directions at very high speeds. And we can pick that up. So that has a wealth of information as well. Okay, so running a bit low on time, so I've got this emergency slide. I thought I might. So, as I said in the abstract, in the summary, I'll just go through a few amazing things that are discovered with Starlight, apart from what I've just talked about, right? There's a lot of amazing stuff in previous slides. Through Starlight, this is Hubble back in the 1920s and 1930s, using a 100-inch telescope, discovered that the universe is expanding using redshift, which I just mentioned. Another thing that's extremely hot topic right now is exoplanets. So these are planets around other stars. So it turns out if you use photometry or spectroscopy, you can actually infer that there's planets, and you can say how many planets. And so this, you'll see you've already seen probably that all these press announcements about, oh, we discovered an Earth-like planet around, phone number star. Another amazing thing that actually I'm working on with my PhD student as well is this star seismology. So it turns out that the stars actually oscillate, they vibrate a bit like a drum. And this is seismology. So the reason we know that we have an iron core is because of seismology, because the Earth vibrates when you have an earthquake. And so these are basically star quakes. And you can work out what's inside the star, the density structure, so you can actually look inside stars. So this is a very hot topic at the moment as well. And again, our previous talk in this series was by Anna Friebel, and she talked about the most ancient stars in our own galaxy. So there's small stars that have been sitting around since the age of the universe, since the universe started, almost 13 billion years old stars. And we use spectroscopy to work out how much, for example, iron is in those. Okay, so I'm going to just do a quick skip. Just yell out if you really want to see something. Well, this is exoplanets, and last year there was a whole heap reported by the Space Telescope Kepler. We now know 1,800. Oh, this was a cool picture I came across online. So this is sort of an artist's rendition. It's clearer over here. It's not so much the lights in the wrong place. Giving an indication of just how many stars have planets around them, and that they're not all the same as our solar system. Some just have one planet, some have one giant planet, some have 10 planets like us, but there's a lot of stars have planets. And we learn about that through, I'll skip over these. There's a vibrating star. And I'll show you this because it's just something that I've been working on lately. So the future of stellar modelling, so modelling stars, is 3D. We're traditionally doing it in 1D, computer simulations. So what I've modelled here is the future sun. So this is when it's a red giant, so in about 5 billion years. And because it's very expensive to run these detailed models of stars, so we've just run a chunk of the inside of the star. And this is what we call a convective zone. It's sort of boiling over in here, and then there's a stable zone across here. So this is later in the sun's life. So it's basically... then your luck, it'll just come up. Not having luck. Okay. I'll skip over that. Anyway, you can see one of the things I've been doing. All right, to come to the summary, because we're getting to the end of the time. So I just want some sort of take-home messages. These are fun facts that have probably bamboozled you with all this information. So basically, stars come in a variety of colours, which I think is really nice. The other main point is the starlight contains a whole heap of information, and we're just starting to decipher all that information. And with bigger telescopes and surveys looking at millions and millions of stars, we're going to learn a whole lot more about the universe in the next few decades. We're looking back in time when we see stars, or the sun. Sunlight is 8 minutes old when it gets to us, and the universe is very, very, very big. And like I said, we're all working hard to try to expand our knowledge here. Final conclusion, stars are vital. They provide a wireless stream of information. So we basically have all these electromagnetic signals coming in. So all those stars you see, and the stars you don't see because our eyes aren't sensitive enough, or they're emitting in the radio or infrared, there's all this information coming down to Earth. And we're slowly picking it all up and recording it and trying to decipher the universe. So without starlight, we wouldn't know much. And the night sky wouldn't be so pretty. Oops. And that's my daughter there, 2-year-old daughter, and she's right into stars. I wonder why. And that's the sun. She's our closest star. Thank you. Alex has got the microphone if we have any questions.
Thank you, Simon. What or how strong is the evidence now to support the idea that globular clusters are the cause of previous galaxies that have been cannibalized by the Milky Way?
That's currently a hot topic. We're still trying to decipher it. And one way to do that is look at our own galaxy and look at... So one of the big surveys in Australia right now is called the Galar Survey. So it's actually Galactic Archaeology, a very Aussie name. And the astronomers take soft toy galars up to when they go into the telescope. Anyway, it's a huge undertaking. So they're going to look at 1 million stars in our galaxy and look at 30 elements in every star. And they're going to try to reconstruct, so they're going to try to match groups of stars that may have come from a particular galaxy that got merged with ours, or particular clusters. So this is an ongoing work. Yeah, we're not sure. We're trying to work out how the galaxies were built up, and yeah, basically it's an open question. And this year there's a conference on that in Germany that I'm going to for that exact thing, trying to work out the history of galaxies. We still don't really know how they formed. But one of the main theories is, yeah, that things kept falling in to these massive galaxies, and that built them up, built their halos up. So.
One of the pictures you showed us was of the Hubble extreme space.
Yep, deep field.
Yeah, deep field. And one of the stars I noticed in the bottom right corner was giving off 2 types of light, a red and a blue one.
Oh.
I was just wondering why that was happening.
I have no idea. Very observant. Where'd my mouse go? My first answer is I have no idea.
Do you want to look for it?
How do I go to escape? Hubble deep field.
Simon, while you're doing that, can
Yeah.
I say that if anyone wants to hang around after the talk, I'll be telling you about a total eclipse of the moon that's coming up in about 3 weeks' time and how you can observe it. So stick around if you're not busy.
Okay. This one?
A couple of centimeters up the word of Hubble.
That's a star.
This guy?
Yeah.
Oh, yeah, that's just a chromatic aberration, actually. So, yeah, it's a star. It's relatively close. So it's a point. Think of stars as point light sources. And when you get point light sources, they have this characteristic sort of star shape when you take a picture of it through a telescope. So it's just an artifact of using a telescope.
Simon, could I give a question from a totally ignorant point of view? How do you determine the difference between a Doppler redshift and a general relativity redshift due to the size?
It's a good question. I'm not sure. I'd have to... Alex, could you answer that one?
It's the difference between...
Observationally, how would you tell the difference between a gravitational redshift and
it's just redshift. That's just redshift. The light is stretched, and that's it.
Yeah, so people working in that field would definitely know. I don't know.
It's the main part of our theory of relativity, that there's no difference.
Yes.
Which represents the
That's what it's about.
within the galaxy.
Yes.
But then you've got a much greater redshift due to its expansion on top of that.
Well, it's due to its just normal velocity. The whole galaxy. So for instance, yeah, we pick a galaxy. The whole galaxy is moving at some velocity. Just things move. Then within that galaxy, all the stars are sort of orbiting around, like we're orbiting around. Our sun is orbiting around our galaxy, and some of the stars are a bit wild, and so everything's moving. But then on top of that, you have the expansion of the universe, which also gives you a redshift. Okay, so usually when you look at a galaxy in Hubble Deep Field, you're not seeing individual stars. You're seeing the sum light of billions and billions of stars, and you can basically look at a very strong line, like I guess calcium or something. They look at and see how far that's moved, and that's really the sum of all the light, and you can see how far it's going away. And those motions within the galaxy are relatively small, so it's the size as well.
Hi, Simon. I've got 2 questions. The
I'll make the first one the easier one. You said that the absorption spectra told you what the star was made of.
Yes.
Surely this would be what the star's light is coming through, not necessarily what the star is made of?
Sometimes the dominant feature in the spectrum will be what's between you and the star. That's true. So this can complicate things. But in space, there's actually a lot of nothing. So the starlight actually quite often comes to us fairly unadulterated. And it depends on which part of the spectrum as well. So if it's dust, then it'll subtract in, I guess, in the infrared. And yeah, so you're right. And this is another technique. So if you have a very bright star or a very bright galaxy way off in the distance, but you have a gas or dust cloud that you want to know what it's made of. So you actually use that very bright galaxy as a background light, and then you can see what gets subtracted out, what gets absorbed by the clouds.
The second question.
These are all complications to my simplistic talk, right? It's not as easy as I made it sound.
I'm quite sure.
The redshift that helps you distinguish between the two. What was the original feature?
That's true as well. Yep. There's.
Redshifted from the
Yep. That's true. They'll have different velocities unless they're nearby.
Right. Now the second question relates really to the nature of the light in itself. Do we assume that all stars emit a continuum of a spectra?
Not necessarily. Yeah, that's sort of an idealistic picture, and they are pretty well modelled by a black body spectrum, like these sort of sun-like stars.
Okay, that leads me on then to what is the wave motion in? We're talking of electromagnetic wave motion. Now, if we take an analogue of, say, water, we can create a wave motion in water with different wavelengths, but the medium through which this wave is travelling is...
It doesn't need anything.
It doesn't need anything.
A vacuum. So the speed of light usually quoted is the speed of light in a vacuum.
Right. Yeah. So what?
Most of space is almost a vacuum.
So what is the wave motion of? Just electromagnetic what? Energy.
Energy.
Energy. And if there was no wave motion, there'd still be energy.
Sort of. Well, I mean, you could have a particle. Like it'd be a different universe. Put it that way.
Yeah. Okay.
That's sort of what defines our universe. That's right. Speed of light in dark matter. If you tell me what dark matter is, I'll answer your question.
Hi, Simon. Just a quick one. Have you been able to use any of your star seismology methods or whatever to analyse or look through our gas planets in our own solar system, or has that already been done?
To see if you can... I was wondering about that myself. Can you... I'm not sure. We need to... so the next talk in this series, in March 31st, is Professor Tim Benning from University of Sydney, and he's an expert in this area, so he's the perfect person to ask that question. So you're asking whether we can pick up our planets. Well, I mean, you can pick up with the photometry method, which is just a planet passing in front of the star, and then because there's something in front of the star, the light goes slightly down. Yeah. That's one method. You can certainly do that with, say, Venus.
Yeah. Right? So I'm just thinking about looking into our own gas giant planets that we've got in our solar system.
In terms of...
seeing what's inside.
If they oscillate. I'm not sure. Yeah, it's an interesting question. I'm not sure if... Not all spheres will oscillate. It depends what they're made of and if there's something that's sort of making them ring.
There are radio science experiments done with spacecraft so that you kind of do the similar sort of style of experiment by measuring the radio waves coming from the spacecraft that would pass around near the planet that it's going past.
Yeah, I think this is sort of radar imaging and stuff, but I think you're talking about seismology of other planets. If they're yeah, I'm not sure. It's an interesting question. Okay, yeah. You can't use that method, that's right. But he's saying just look at that, point your telescope at Jupiter itself and look at that. But there's another way using spectra to detect planets, and I imagine Jupiter's pretty obvious in the sun spectrum. I'm not sure.
It might be a simple question. I'm just wondering how do you know how old light is? So you say that's 13.2 billion years old that we're looking at. How? What's the mechanism
That's in the redshift. So basically, I'll go back to the redshift. So basically, it's if the spectrum shifts, the further away it is, and this is due to the expanding universe. That's not the redshift, that one. So this is what Hubble discovered in 1920s, 1930s. Well, it's not exactly this movement, it's actually the expansion of space. So everything is moving away from everything else because space itself is getting bigger. And that gives it a sort of cosmological redshift rather than just a normal velocity redshift. So it's basically, if you look at a spectrum, so this is the rest wavelength, so if the star was staying still relative to us, and this is the spectrum if it was moving away at a great speed. And basically, the further away things are, the greater this redshift is. And so we can say how fast it's moving. And then that's cosmology. So not very well explained.
Does this answer your question? Okay. So let's thank Simon one more time. Assume now the ASV meeting starts.
And just to remind everyone that, sorry? Oh, yeah. Just for next week's talk, as I mentioned to someone just then, we've got Tim Bedding coming, not next week, sorry, 31st of March. And he'll talk about this particular space telescope that's been looking for planets. But it turns out you can get a lot of detailed information about stars as well, which he'll talk about. Thanks for coming.
Thank you, Simon.